Ready. String Theory by Mary Peeling. From the kitchen window, the garden hose is a thin green line. We don't notice the way it curls inside, hiding more than it shows. Dimensions flatten with distance like plant matter in a terrible drought. It's been so hot, Antarctica cracked in two. I wonder what the panic decided. Coiled as secrets inside a marriage, the Earth has interior shape. Bound into a space so small, it unites electromagnetism and gravity. No place for resentment or annoyance. Lies grow white and disappear. I water the roses and the artichoke. Extravagant, lavender, needier than it looks. Here, at the horizon of theoretical extinction, we cut flowers for the table. We've seen the way weary mourners do, praising geometry as if miracles could happen. All right, that was a great poem by Mary Keelan. Not quite sure who that is, but hey, I thought it was interesting throwing some random mathematical words in there, and I don't know, just the title, right? As you guys can probably guess, let me put my face up.
It didn't seem to really talk about string theory very much.
You are correct. The disembodied voice is correct. It did not really talk about string theory much, which is, I think we can actually talk about it during the actual show.
Hey, wait a second. What is it? What are we watching?
What are we watching? All right, you are watching SG2 on Space, the only weekly space show. I am still going to go with that because, let's see, the only weekly space show. You can go on youtube.com/eshingo/streams to look up SG2 on Space. So I'm going to, let me see here. This guy right here is Leonard Kramer. How's it going? You're muted. Since you're muted.
And that's Shen.
That's right. All right, so before I go on, I will always just say, hey, support the show, patreon.com/SG2 on Space. Thank you, Kyle Baker, Sam Welsh, John Graves for the kindly donations. I will keep that ticking in the background or down below. Nice headband, Leonard. It's blue.
Thank you. It's blue.
It is. All right, so this is episode 207 wow, that's quite a while. For anybody who's watching this live, today is April 17th, 2024, by our current Gregorian calendar. But without further ado, we want to talk about what string theory is. I think a lot of people have heard of it.
Right.
And then, the poem I just read doesn't say anything about that. But what? Let me just ask you this: what is it?
Yeah, I thought maybe you'd ask me that.
Well, I'll just say what I know, which is it's some kind of theoretical framework in which instead of defining things as particles, like in the standard model particle physics, right?
Yeah.
Replacing that by entities called strings.
Yeah. So there has been this desire, so like even in ancient times, in ancient times or medieval times, people, they wanted to classify what is everything about, what is the universe made of, and so they, in ancient times they said air, fire, water, and earth or something. So we've always been forever trying to understand that or try to postulate what things are made out of, and then we have these different forces and we want to try to unify them. So for example, like Isaac Newton, he discovered that the gravity that when something falls, it's the same force that is causing the moon and the planets. So this is like so unifying all these forces, and so this has been very successful up through the 19th century with the Maxwell's equations for the unifying electricity and magnetism, and we've been doing a tremendous job of that all the way into the 20th century. But there's one force we haven't been able to unify, and that is, do you know?
Yes, I do know. Gravity.
Gravity.
So the 4 fundamental force. Okay, so at least I know
Yeah.
the electromagnetism, strong force, weak force, and then gravity.
And then gravity. And so we have been able to. We think that we're able to. We have a phenomenal a verified theory about the nature of matter that kind of unifies the fundamental forces that contribute to the standard model that we talked about, which is, has to do with the things that atoms are made out of, the electrons and muons and neutrinos and so forth.
Mm-hmm.
But gravity is not a part of that picture at all, and because gravity is such a weak force that if the particles would have to be so close together in order for the gravity to have an effect in the classical sense, that there just is no hope of ever observing anything like that. However, there is a theory. People have worked hard on this. It's a very complex mathematical theory, where the notion is that what things are made out of are these things called strings, and a string is sort of a unified element that makes up all things. So, for example, an electron is thought to, it's never been observed, but it's thought to manifest a string deep down inside of the electron. Likewise, matter like protons and neutrons are made of quarks, and it's thought that the quarks are made up of something fundamental like that. And they have a different, they vibrate at different rates. The size of these strings are thought to be in proportion to in proportion to, for example, a proton. The size of the string would be, let me put it this way. If a proton were the size of the solar system, these strings that we're talking about are the size of virus particles. So it's like, yeah, it's like 30 or 25, 30 orders of magnitude, 32 orders of magnitude smaller than that. And the theory incorporates multiple dimensions, new dimensions, which I have to say I don't understand. I mean, I don't understand really what they mean by these extra dimensions, but apparently they're coiled up. They need 6 other dimensions in order to get in order to get something that will emit these gravitons. In other words, in order to put gravity into the model, the 6 dimensions, they coil up into a kind of manifold that's called a Yai-Calabi manifold. Those are two people that.
Can you explain a little bit what manifolds mean?
Well, it's like well, we know about 3 dimensions. So you have a matrix. You have 3 axes that come together, and then you can have. I think we can understand a 4th dimension would be time. So we understand that. So that's essentially a manifold. But these there it is, the Calabi-Yau manifold. It incorporates all the other dimensions, and they're all curled up in some fashion. And these are necessary in order to incorporate gravity.
I think my math is too primitive. I don't.
I think my math is too primitive too. I'm still working on this. I do have some kind of ambition.
I got to learn differential geometry.
So I feel comfortable with general relativity now. With Einstein's theory. I'm pretty comfortable with working with quantum mechanics, but that's what this does, is it brings quantum mechanics and gravity together. Now, one of the big criticisms of it is that it makes no it has not made any verifiable experimental predictions, and so that's an issue. That's a real issue. So now now it is true that there is a theory, or an adjunct to this theory is something called supersymmetry,
What's
or
that?
I'm sorry, superstring theory. And so one of the outgrowths of this is that many of the fundamental particles that are in the standard model is, we've talked about it before,
Yes.
is sort of like the fundamental particle periodic table. So we have electrons, neutrinos, quarks. There's 3 different kinds of quarks, and then there's bosons, which are things like photons and other kinds of particles that transfer forces back and forth. And then there's 3 generations of those. So we have, so there you can see over there, you can see standard model. So there's 3 kinds of quarks. Those are the purple things, and so forth. So I'm not quite familiar with that format. So those are the forces that have to do with so supersymmetry postulates that there's these conjugates to each one of these forces, and that they will have a different mass. So the fundamental particles that have a small mass have associated with it a kind of alter ego particle with a very, very large mass, and it was thought that the Large Hadron Collider in Europe might have exposed those. They were able to produce the Higgs particle, and the Higgs, that's called the Higgs boson, and that's the part of field theory that gives all these particles mass, and so that part of the theory is confirmed quite nicely. So we think we understand everything going on, practically everything going on over on the left side. But these other particles on the right-hand side, where it was thought that the Large Hadron Collider would have enough energy to perhaps produce these particles, out of energy, out of the collisions that it produced, and nothing was seen. And so it's really actually quite a blow to the string theory.
I mean, are you saying that they anticipated like not just the Higgs boson, but also like some of these? You said these other particles that string theory said, hey,
the particles on the right there,
right,
they're all super symmetric versions of the particles on the left, but they have different masses, and none of them were observed.
That's
and so it's people have to sort of recalibrate their theory.
It's I think you mentioned this before, that this theory, has an issue where you're trying to fit reality to this theory versus this theory actually predicting something.
So as I understand, the nice thing, and I've read a couple books about this now.
Mm-hmm.
The nice thing about this theory is that it's phenomenally consistent with this idea of a what do you call it? Gravity, a graviton. So in other words, the force carrier for gravity is consistent. So it's a nice consistent theory in that respect. But we don't have any theoretical. We don't have any theoretical. I mean, we don't have any measurements to verify it, and so it's vulnerable to this accusation that it's not science anymore, right? Okay, now I've kind of gone along talking about the the full up mature string theory. But the history of string theory actually does go back. There is a kind of a primitive string theory that has to do with these things called hadrons. Hadron are the subatomic particles that make up just the atom. So protons and neutrons. and anything that's made up out of quarks. So actually, I guess maybe can we let's talk about the history of where this idea about the quarks go. I'm kind of changing gears a little bit. I'm going back in time to the.
Let's go back in time then. Okay, so
we're gonna go back in time to about the late '60s, or actually maybe after the Second World War. So
go ahead.
Yeah. So after the Second World War, we had the atom bomb project. The Manhattan Project to develop the atom bomb, and there was a lot of interest in atomic physics. And actually, the way what I've learned is about the history of this is that the Atomic Energy Commission in the United States, they wanted to continue to maintain a kind of cadre of well-trained physicists because the Manhattan Project was so successful, and they poured a lot of money into atomic physics. Trying to understand the fundamentals, so a lot of these what they call synchrotron accelerators were developed. If we go way back to Rutherford, back in the 1910, 1920s, atomic physics was developed. In other words, we started to understand the structure of the atom, protons, neutrons, and electrons. And Rutherford did this by firing particles into a piece of foil and then looking at whatever gets backscattered. And so the physics community in the 1940s and 50s and up to the 60s, they continued that sort of tradition of building bigger and bigger accelerators and smashing atoms together in order to produce, and the idea being that if a proton has some kind of structure inside, that we'd be able to see it by smashing them together. And it's interesting that Rutherford's atomic apparatus for investigating just the nature of the nucleus would sit on a desktop or maybe on a lab bench, and then by the end of the Second World War, and going on into the 50s and 60s, the particle accelerators had grown to the size of, they needed like railroad cars to move them, and they were a kilometer long. These huge devices that were needed to accelerate accelerate protons to or electrons to very high speed. In order to get higher and higher energies, in order to look at smaller and smaller objects. So in the 1950s, what they discovered was that if they collide protons together, they would get just this. I see it described as a zoo of particles that were coming out, just all different kinds of things with different masses and different angular momenta, different spins. It was like a big mess. They called it like a subatomic, it's a subatomic zoo of particles, and so people took these two. There was kind of like approaches to it. They were trying to classify them, and then also trying to figure out something about the internal structure just by playing with the numbers. So that's Murray Gell-Mann's eightfold path. What you just showed there was Gell-Mann. He was doing something like a numerology,
eightfold path. That sounds very spiritual.
Yes. Well, Gell-Mann, he was being cheeky about that. He was well known for coming up with very obscure literary references and
eightfold path.
Yeah.
It's like, anyways, go on.
Right, but so when he put this thing together, so the corners of each one of those of that hexagon are subatomic particles with certain kinds of characteristics, and one of them is called isospin, and the total energy, or it's different kind of quantum numbers that are associated with it, and he was able to organize them on this Cartesian graph this way.
This Cartesian graph.
Right. So. It's actually a Cartesian. It's a graph. It's an XY plot, but the particles organized that way. And so he found one of those particles. I don't know which one of them was missing, had not been observed. So those were all particles that had been observed by about 1964, 63, 64 when he was working on this. And he said one of these is missing. And he was in a conference, and where he presented this, and he says, "You guys need to look for this particle." Talking to the experimenters, and they went out and they looked for it, and indeed they found it. And so that was a big validation of. And so what he's finding is that he's the one that came up with this idea about three. There was three particles inside of the proton and three inside of the neutron.
Right.
And he called them quarks. And it came from, that's the tenfold way, or 10, something like that. So anyway, this is what he was doing. He was just playing with the numbers in order to see if he could figure out a structure. And out pops this idea that and he postulated that, well, if there's such a thing as these three different kinds of particles, that and he actually they used these, like they tried to use kind of interesting names for them, but he came up with the name quark for these. And the quark comes from a literary work by James Joyce, and it's called Finnegan's Wake. And I don't know the story of Finnegan's Wake.
That's really interesting, but go on.
But there's a phrase in there, say, what is it, like three quarks for muster May, or something like that. We can look that up. But so he came up with that. Now he had a colleague that came up with almost the same theory, but was not as experienced as him. I don't know who that. I've forgotten who that was. But
Gilman and Zweig.
So Zweig was younger than him, and all of his work, he called them aces. He called the correspondence of quarks for Zweig was aces.
Active for playing cards. Wow.
Yeah. So and so none of his stuff didn't get published, and principally because I think that he didn't know how to go up against the paradigm correctly. He tried to say that these were real things, and it's the nature of the universe, or he tried to assert that some reality to it, whereas Gell-Mann was much more modest and said, this is a nice numerical device that allows us to, sort of number sort of enumerate or elucidate the internal structure of protons and neutrons. And I'm going to tie this to string theory in a moment. If we
ties in.
We're getting there. But he was more modest about it, which is, that's like a good thing. The principal problems with it was that, those three charges, those three quarks, they have electric charges that are multiples of a third. So they come in 1/3 or 2/3 electrical charge, and nothing like that had been observed in anywhere. And then there were some other issues that with it that made it a little bit far-fetched. You never observe a quark, all by itself. So 3 quarks for muster mark.
Sure,
that was what it was.
Much of a bark, and sure, any he has is all beside the mark. Okay.
So it's like so I think it's like a meaningless word, and Gell-Mann really liked it, and actually I think it is kind of a good thing to call them, So, but
yeah, sorry,
anyway, that's the story about that. But anyway, so in addition to the quarks, Okay, the quarks themselves seem to have relatively small mass, okay, compared to the size of the protons. So there's three of these quarks. Three of these quarks. It happens that there's also other generations of quarks that are observed in particle accelerators, but they're held together. They're held together by the strong force. The strong force is mediated by these particles called gluons. Okay, so that's a really good name for them. And the gluons manifest, and what happens is, if you look at the particle zoo that we talked about earlier, if you look at the spin versus energy, so if you can spin something, right, it means, and you can detect the spin, it means there's something inside of it. There's some kind of structure internal to it. So if you were to characterize or organize the energy versus the spin of these, or the angular momentum of each of the particles in the zoo, so it's like these the quarks are held together by gluons, and then they seem to organize along a linear string or a rope, or something of that nature. And so that's really what motivates the string theory. This is not the string theory that we were talking about in the beginning of the show. This is the string theory. This is the string theory. This is a kind of string theory that's associated with, I guess it's chromodynamics. I guess we're talking about quantum chromodynamics, right? Yeah, so we're talking about quantum chromodynamics. And so what we find is that if you organize all of those particles that are coming out from those experiments in the 50s, they were sort of like energized or special. A number of them were special complicated versions of either what they call mesons or the hadrons that we've been talking about. So they're held together, and they behave as though that they're held on a string. In other words, if you have two masses that are together, I mean, I'm talking classically. If you have two masses attached to a string and they're rotating around, then the angular momentum, which is related to the spin, will plot. As you increase the energy, it will go straight up like a straight line. If you had something else, like some kind of complicated thing, like a solid ball, then it would follow a curve. The spin versus energy graph, you graphed it. Well, these particles were following, or the certain class of particles were following along a straight line on the energy angular momentum energy graph. And that's what made people think that the gluons were getting strung out along a linear structure that held them together. And furthermore, you could not break it. In other words, the gluons, the quarks could not exist by themselves. If you broke this string or you pulled it out, then the quark would immediately pull another quark out of the environment and create another one. So anyway, that linear thing is something that's well observed. So that does produce well validated theoretical observations that are consistent with the Gelman theory of the standard model. And so I believe that observation motivated the merging, the theory that merges gravity with the standard model, but it required strings that were 30 orders of magnitude smaller than what we see in the hadronic space, as it were. And so that's
I would love to understand the mathematics of this paper like this.
Yeah, so
Huh.
Yeah.
Yeah.
So that's what I wanted to talk about. I wanted to I wanted to do a little report on some of the reading I've been doing.
Yeah. How's so you basically you divulge your knowledge based on the readings you've done.
That's correct. Yeah, I never took a class in string theory or anything like that. So
I've
I mean,
only
I did take classes in the hadron, in the standard model.
Yeah, of
Okay,
course.
but
That's
but
physics. To be honest, yeah. When I got my degree, the standard models. I suppose that's what was assumed. String
yeah,
theory. I don't know if that's part of the curriculum of.
I don't
I don't think
I don't
so.
I don't think so, and I think it is controversial because it makes these predictions of you can kind of whatever you observe you can adapt the theory. And another thing that's missing are the fundamental constants, like the masses of things, the gravity constant, the fine structure constant.
That's why we haven't moved away from the standard model yet, right?
So we don't. Well, the standard model is well validated. It's just that we still don't have a theory that gives us the fundamental numerical constants. In other words, gravity. In other words, the Newton's constant.
Mm-hmm.
Okay, the um, um, the um, the electric field constants. The fine structure constant. Effectively, we don't have a theory that produces those, and as far as I know, nobody's even working on those. And so it's that's physics. That's where we are.
That's where we are. That's physics.
Yeah.
So, do you have any
So
good recommendations of books based on the accumulated knowledge?
I read a book by I read a book by a guy named uh his name is Kaiser, David Kaiser. Okay, and he's a professor of physics at MIT, and he does um I read a book by him. And it's actually an anthology. It's a lot of essays that he wrote. It's not a lot of math, but he really likes to talk about the history and yeah.
Well,
They
guy is Garmin Schausen Professor of the History of Science. So
yeah.
I guess that's what you're
I read some of it's motivated by Leonard Susskind's book that I read, which was the Black Hole Wars.
That's right. Black
And
hole.
then you can also read An Idiot's Guide to String Theory.
Ooh.
And
Are you recommending? Are you saying most people are idiots?
no, it's just a fun book. Okay. And it's by.
That's so funny.
It's written by a very good science author named George Musser. It's the complete idiot's guide to string theory.
Yeah.
Yeah, and it's actually a pretty long book. But I do like David Kaiser.
What was the book by David Kaiser?
The book by David Kaiser is let me check. I have my Amazon thing open.
Quantum Legacies, right?
What?
Is this it? Dispatches from an Uncertain
Yes.
World.
Yeah.
Okay.
Quantum Legacies. Yeah.
So Quantum Legacies, Dispatches from an Uncertain World.
And he also has some lectures at the MIT academic site. He has a whole course that's recorded and you can watch. And I want to say he seems like a really nice guy. He just seems like a really nice. When I watched some of his videos and interacting with the students,
He seems like a nice guy. I mean,
He seems. I know it's easy to say that about people, but he just seems like a really, you know, I don't mean it in any pejorative way at all. I mean, he seems like a very nice. He'd be a really great guy to be a professor, and also it's a great course.
the other one you said is by Leonard Susskind.
What?
No, not Leonard Susskind. What's the other one that you said?
Yeah, Leonard Susskind. That was the one by. That was the Black Hole Wars, and he goes into. I think I'm a real fan of Susskind because he really does want you to understand. You know, he started life as the son of a plumber, and his dad wanted him to be a plumber, and so he comes from that kind of background.
Yeah.
And so he wants you to know, he wants you to understand, and he goes to the trouble to try to explain all of that. But we did the Black Hole Wars some weeks ago.
We talked about Leonard talking about black holes and such. Yeah. Okay. I did not know that he was the son of a plumber. Maybe you talked about it then. You probably did.
Yeah.
Oh, Leonard Susskind wrote a lot.
And I don't, he seems to, if you read his books, he's
recommendations from Dr. Leonard Kramer here on trying to understand string theory. It's the Complete Idiot's Guide to String Theory.
Yeah.
And then Quantum Legacies, Dispatches from an Uncertain World, and then lastly, The Black Hole War, My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics.
Yeah, and
3 different novels.
And I'm still reading about this, and I'm still hacking away at it.
Which one are you reading now?
No, I'm about ready to pick another one. I'm not sure yet.
Okay, and just for our audience's knowledge, these are not mathematically heavy books. It's for
In fact, I'm kind of looking for one with a little bit more math. So, no, they are not. These are popular books that anybody can read. Even Professor Suskind's books, and David Kaiser is he's the class that he teaches. He's like a dual kind of professor. He's a professor of physics. I think he studied physics, but he's also interested in history and the history of physics, and particularly of the 20th century. And he's researched a lot of these things himself. He's gone through and looked at Einstein's papers, and
he has a Leviton Prize in Humanities and history.
Yeah. I think he's quite a treasure for MIT.
Yeah, so he can write like history and also theoretical physics.
Mm-hmm. Yeah.
Lovely.
Yeah.
Oh wow, that's a lot of publications. Okay, but anyways, that aside, okay, thanks for that note. We are over time now, but I want to talk about something I'm somewhat interested in.
I look forward to this every time it's a highlight of the show, I think.
Where's my UFO? See?
Yeah.
So I gotta pick up some cows. How do I?
I don't know. I have
Do you see this?
I have half a coconut shell.
Do you see this?
Yeah, I see it.
All right, okay.
Yeah.
All right, with that segment, let's go. Okay, this is in 2020. I've supposedly a bunch of UFOs over. Let me see if I can power this thing down. Wow, that's pretty good, Leonard.
It's a coconut.
UFOs over.
Just use them as little dishes.
Over Tokyo, Japan. I've not seen this yet. Let's see. Let's see if you can believe it.
That's Gamera.
No. Here, let's see it.
No.
So what is happening there?
There. Those are flares. It's been dropped by an Air Force plane.
What could that be?
They're flares. They're flares on parachutes. It's probably a military exercise. I've seen this kind of thing before.
Really?
There was another one. Yeah, the plane just dropped another flare.
That's your answer? That this is a flare?
Yep.
I don't know. It's not really
They're
moving.
all flying.
Aren't flares supposed to move? No?
They're on parachutes. Let's watch. I mean, they should gradually fall. I think there's some evidence that the second one on the left seems to be dropping down behind the building. Oh, and somebody cuts it off. See?
Yeah, it is falling.
Yeah, I've seen this kind of thing before. This is some kind of Air Force exercise, and they were dropping flares.
Okay, so this was a group of 6 UFOs in Tokyo on July 17th, 2020.
Yeah.
The objects from his balcony. UFO hovered around 15 minutes before they disappeared one at a time.
Yeah.
Okay, well, in that case, I guess that's resolved then. Well, that was easy.
Yeah, I mean,
there's nothing else to it. Wow. So, well,
sorry.
you know. Okay. Just cause I do one more.
Okay. Hey, you know, we ought to ask the audience what they want to hear us talk about.
I have.
We ought to get people to write in.
Okay, look at that in the clouds. If that's not some alien creatures, what could possibly be?
I would say that's definitely alien creatures. It looks like art by like a surrealistic sculpture by like Max Ernst, or looks like yeah.
Okay.
That's pretty impressive. That looks like some kind of, like I said, that looks like a sculpture that Max Ernst.
Yeah, mysterious picture of figures.
Surrealistic.
This is January 2016.
Wow.
Wow.
Of course, maybe it was created by ChatGPT. You see how we don't believe anything?
We don't believe anything because you can make up anything these days.
Right. We don't believe anything.
I
don't know what to say.
I don't know what to say, how we can actually...
Yeah.
All right. Anyways, I don't know. I mean, yeah. All right. So I guess I will have to see a realistic video to believe it.
Yeah.
That cannot be explained away by Leonard here.
Yeah. Well, I'm not really into debunking these things. It's just that.
Okay, you're just saying what you think.
I'm just saying what I'm thinking, and you know, like when Oumuamua, which was that asteroid that came in 2017, 2018 from interstellar space, and it was making funky maneuvers. I mean, I conceded that seemed to have the attributes of an alien presence, you know, some kind of alien technology that it did have those, you know.
That is very true.
You know, and then you know, the argument that you know, extraordinary claims, it's an extraordinary claims and requires extraordinary evidence. Well, the claim, I mean, all you hear is how omnipresent life is, you know, how ubiquitous it is all through the galaxy because of the law of large numbers. You know, there's trillions of stars, and around almost every one is a planet, and so some fraction of them must be amenable to the establishment of life. So life must be ubiquitous throughout the galaxy, right?
Then why would you discount
that? Right. The extraordinary claim is that it's not. You know, it's not. Or you could make that case. You know.
Yeah, I can see what you mean. I mean, like the same person who argues for the fact that due to the law of large numbers, that you do have all these extraterrestrial life out there, they may also be the same people who argue against.
They're.
So it's kind of victory. So,
yeah, you can't win. So, yeah. But having said that, I'll repeat it, and you're not going to like it. But it's like I don't think there are any.
I know you find it that even we exist.
I believe I think it's a fluke that we exist. Yes, it's
Yeah.
and I think even though there is a large number, the number is not large enough. Okay, in order to generate a living structure from abiotic matter, just spontaneously emerging, even after millions and millions of years. So
All right.
yeah,
According to you.
according to me, yes.
According to you, yes, of course.
Mhm.
I hold a different opinion, but
Okay,
we
doesn't
shall.
matter. I mean,
Yeah. All right. With all that said, we've gone way over time. You guys, thank you for watching. This
Yep.
has been SG2 on Space with Dr. Leonard Kramer. This episode 207, Fundamentals Behind String Theory, where we touched a bunch on not just string theory, but also the origins of it, which stems from back in the 60s. So Leonard went all through all that, and we have some book recommendations for you guys as well, so you can take a look at the comments. And
yeah, leave comments.
I will say, leave comments. Leave comments. We like comments.
Yep.
Leave comments.
Especially from 10,000 years in the future.
Yeah, if you're 10,000 years from the future, you should really leave some comments and make it somehow clear that you're actually from 10,000 years in the future.
Yeah.
I'm not sure.
We'd appreciate it.
Yeah, yeah. So with all that said, all right, so everybody, SG2 on Space, you can go share it there. Support the show. Patreon.com/SG2 Space. Thank you, Kyle Baker, Sam Welsh, John Graves. And
subscribe, send links to your friends, and so forth.
And yep.
Oh yeah, we need to do our nerd gang sign.
I don't know why I did that. Oh, that could be a nerd gang sign. All right, okay. So I'll do what Leonard does, which does this and then says
Namaste.
Namaste.
Okay. Shalom. And mwah.
I knew. You can't stop without that.